Hello everyone, welcome to my channel. Now in this video I am going to discuss the topic the pressure difference in bubbles and liquid drops, and then I will apply this concept in deriving the Jurin's law, that is the ascent formula, and thus explain the concept of capillarity, that is the rise and fall of liquid inside a capillary tube. Now see, one of the consequence of surface tension is the bubbles and liquid drops are spherical in shape. Now as we have seen, the molecules of the surface of the liquid, they have this excess energy, and in order to minimize this energy they try to acquire the minimum area. Now for a given volume, sphere has minimum surface area, so it is for this reason the liquid drops and bubbles, they are spherical in shape. Okay, now there is one more consequence of surface tension, that is, see, when the bubble or this liquid drop, they acquire spherical shape, so there is one external pressure which is trying to crumble the drop, which is trying to break the drop into small droplets, or which is trying to break the bubble. But the bubble or the drop, it is in stable position, so that means the inside pressure, it must be greater than the external pressure. So this is one consequence of the surface tension phenomenon, that the pressure inside is always greater than the pressure outside. Now suppose you have a liquid drop and its radius, it is increased from r to r plus delta r. Okay, so that means if the radius is increased through delta r, so that means some extra energy is spent on the drop. Now suppose you have a liquid drop of radius r. Okay, so if this radius is r, its surface area is 4 pi r square. Okay, now if the radius is increased to r plus delta r, so now the radius is increased to r plus delta r, so now the surface area will be 4 pi r plus delta r square. So what is the increase in surface area? Increase in surface area delta s is equal to 4 pi r plus delta r square minus 4 pi r square. Okay, now if I apply binomial theorem over here, so delta s is equal to, if I take 4 pi r square common, so this is 4 pi r square 1 plus delta r by r square minus 4 pi r square. Okay, now obviously this delta r is very small, so delta r by r is very much smaller than 1, so I can apply binomial theorem. We have delta s is equal to 4 pi r square 1 plus this is 2 delta r by r minus 4 pi r square. Delta s is equal to, this is 4 pi r square, this is plus 8 pi r delta r minus 4 pi r square. So this 4 pi r square term is cancelled. Delta s is equal to 8 pi r delta r. So this is the increase in surface area. So this is the increase in surface area. Now see, this increase in surface area, it is, this work done is against the surface tension. Surface tension is trying to minimize the surface area, but we are increasing the surface area, so that means we are doing some external work. Okay, so this external work is stored as energy, so that energy, it is equal to this surface increase in surface area multiplied by the tension. Okay, now this tension in your NCERT textbook, this, instead of T they have used the symbol SLA. This is surface tension for the liquid air interface. I am using the symbol T, but both are same. Okay, so this energy, this will be delta S is 8 pi r delta r into T. Okay, now where does this energy is spent? This energy is spent against the pressure volume work. Okay, against this pressure difference. Okay, so for this drop, if the radius is increased from r to r plus delta r, and Pi is the pressure inside and P naught is the pressure outside, so this work done is against this pressure volume work, or we can say that this work done is stored as this pressure volume work. So this work is in equilibrium with the work done by the pressure volume work. Okay, so what is the pressure volume work? that work done, it is difference in pressure Pi minus P naught, difference in pressure multiplied by the increase in volume. Okay, now volume V, see V is 4 by 3 pi r cube. This is the initial volume. Okay, so this is delta V is equal to 4 by 3 pi r cube is 3 r square delta r. When the radius changes by delta r, delta V is the change in volume. So what is this? This 3 cancels out. So delta V is equal to 4 pi r square delta r. So this is the change in volume. So pressure difference, this is the pressure against this change in volume. So this is the work done, P delta V. So this is P. So 4 pi r square delta r. Okay. So this energy is in equilibrium. This energy is in equilibrium with the work done by pressure volume work. Okay. So that means these two terms are equal. So that is Pi minus P naught into 4 pi r square delta r is equal to 8 pi r delta r into T. Okay. So this delta r cancels out. So this is 4 pi, this is 2 r square, this r gone. So we have Pi minus P naught is equal to 2T by R. So this is the expression for the pressure difference in case of a liquid drop. It is 2T by R. R is the radius, T is the surface tension. Okay, now this is for drop. So that means for soap bubble. Now soap bubble has two free surfaces, one the inside surface, the other one is outside surface. So for soap bubble, this pressure difference expression, see for one free surface this is 2T by R. For two free surfaces it will be two times this. So for bubble it will be Pi minus P naught, it will be equal to 4T by R. Okay, so this is the expression for difference in pressure in case of liquid drop, in case of soap bubble. So next we will try to understand the term capillarity, and we will try to understand how this liquid rises or falls inside a capillary tube. So now this word capilla, this word capilla is a Latin word. It means very thin, like hair. Okay, so capillary tube is a tube which is very thin, and now we'll also see that if the tube is very thin, the rise of liquid inside the capillary tube or the fall of liquid inside the capillary tube will be very much. Okay, now this your fountain pen and the rise of liquid or water in case of plants, it is all these things are based on the phenomena of capillary tube. Okay, so and in chemistry also in some tests you use this capillary method to identify some chemicals. Now this capillary tube, when this tube, so now I'm going, while drawing I'm going to magnify that size of the capillary tube. So suppose this is the capillary tube. Okay, but usually it is very thin, it is thin like a hair. Okay, and this capillary tube is dipped in a tub containing some water. Okay, and the liquid, now if this is glass, capillary tube is glass and this is water, the water will rise inside the capillary tube, and this action is due to the surface tension. Just now we have seen that for in case of a drop or a bubble, there is a pressure difference between the inside and the outside, and inside pressure is always greater than outside pressure, and the consequence of that is the rise of liquid in this capillary tube. We will see it now. So for this system, suppose this level of liquid inside the capillary tube, it is H. Okay, and this is the surface. Okay, now for this surface, this is the atmospheric pressure PA, and this is outside this surface, means for this sphere this point is outside, so this is P naught. Okay, and we consider 2 points which are at the same horizontal level. This is A and this is B. Okay, so just above this meniscus, the pressure is PA, the atmospheric pressure. Below this meniscus, the pressure is P0, and this is B. A and B are at same horizontal level, and this height is H. Okay, so just now we have seen that this inside pressure is greater than the outside pressure. Okay, so see, for this spherical part, don't consider that this is inside the liquid. Okay, we have to consider the spherical part. So for this sphere, so this is the radius of curvature. It is the center is on the upper side. So for this sphere, this is this point is the outside point, this is the inside point. So this pressure is greater than this pressure. So PA minus P0 is equal to 2T by R. Okay, T is the surface tension and R is the radius. Again, remember that T in your NCERT textbook they have written as surface tension. T is the surface tension. It is written as S, surface tension for liquid air interface. See, okay, both means the same. Achha. Now what is this R? R is the radius of this spherical meniscus. Okay, so if I redraw this part over here, so this is the meniscus, this is the center of the meniscus, center of this spherical part, and this is the center of this tube. This radius is A. A is the radius of the tube, and R is the radius of the meniscus. Okay, this is the tangent at the point of interface of the liquid and solid and the air. Okay, and so this angle, if I draw a tangent at this particular point, this is angle of contact theta. Obviously this angle and this angle will be equal. Okay, so from this triangle I can write cos theta is equal to A by R, or I can write R is equal to A sec theta. Okay, if I substitute this value over here, I have PA minus P0 is equal to 2T by A sec theta. Okay, or I can write it as PA minus P0 is equal to 2T cos theta by A. Okay, acha. Now this is PA and this is P0, atmospheric pressure. This is P0, pressure just below the meniscus. Okay, now what is P0? See, what is the difference in pressure between these 2 points? PB minus P0 is equal to H rho G. These 2 points are at same horizontal level, so that means PB is equal to PA. So instead of PB I can write PA, but this A is exposed to atmosphere, so that means PA is equal to the atmospheric pressure, so I can write this as PA. Okay, see this PB, it is equal to PA, A point A and B are at same horizontal level, but this A is on the surface of the liquid which is exposed to atmosphere, so it is equal to the atmospheric pressure. This is atmospheric pressure. Okay, so PA minus P0 equal to H rho G, and PA minus P0 equal to this formula 2T cos theta by R. So this implies from these 2 equations I can write H rho G is equal to 2T cos theta by A. Okay, and or H, this gives H is equal to 2T cos theta by A rho G. Now this is called the Jurin's law. This is called the Jurin's law. So from this Jurin's law we have this observation that H is inversely proportional to A. Okay, of liquid inside a capillary tube, it is inversely proportional to the radius of the tube. Okay, that means smaller the radius, greater the height. Okay, another implication of this expression is for glass water interface, this angle of contact theta, it is less than 90 degree. So when cos theta, this theta is less than 90 degrees, that means cos theta is positive, so height will be positive. That is for glass water interface, theta is less than 90 degree, so cos theta is positive. Cos theta is positive. So since cos theta is positive, so height is positive. So height positive means the level of liquid inside the capillary tube will rise up. the liquid will go up inside the capillary tube. For mercury glass interface, we have seen that this angle of contact is greater than 90 degree. Okay, theta is greater than 90 degree. So if angle of contact is greater than 90 degree, this cos theta will become negative. Cos theta will become negative. So if cos theta is negative, height will be negative. Height is negative. So when you have mercury and mercury with this capillary tube, then inside the capillary tube, the level of mercury will be depressed. Okay, it will go down, showing this H is negative. So these are the few implications of this expression and how this H varies with A, how this H varies with theta. So I hope this concept, the pressure difference concept and the application of this pressure difference on capillarity is clear to you. Best of luck.